psychological stress forces the body, particularly the liver, to make sugar.
This is the beautiful part of science. If you read a paper like this, it's incredibly impressive.
How do these findings shed new light on that phenomenon?
It's one of the challenges of type 1 diabetes, because with type 1 diabetes,
there's going to be a whole species of diabetes that will be enriched in, say, people
developing the ability to turn on and off parts of your brain. This paper elucidates something incredibly novel. We have known for some time there's different forms of diabetes. What this paper illustrated...
We have our first return guest with us on the platform this morning, Dr. Koutnik. So welcome back. Thanks for joining me.
Hey, Nick, it's an honor to be here. I'm excited to talk about some unique new papers that have recently come out that are of interest to both of our scientific fields.
So the first paper I want to discuss, I want to jump right into it, was published just recently in Nature. Basically, high level, it shows that stress, psychological stress, forces the body, particularly the liver, to make sugar, make new sugar and churn it out. So my questions to you are twofold. First, when you read this paper, what was your immediate reaction as a scientific mind? And second, what is new about the mechanism discovered in this paper?
Yeah, so my first reaction was apprehension, Nick. I thought, okay, is it really going to elucidate a novel model or fascinating new finding? And when I actually read it, I was blown away, actually. It was quite fascinating because they discovered a direct mechanism by how stress induces not just this breakdown of stored glucose. This is how we think of stress-induced glucose elevation. We think, okay, it causes stress. Your body starts breaking down glucose immediately, spilling into the bloodstream to mobilize nutrients for, let's say if you're running away from a lion or a dinosaur, whatever the analogy might be, you want to mobilize those nutrients immediately so that you could have it for your ability to survive that moment, right? That's what your body is built. But this mechanism specifically shows a novel way in which it does it, where the stress specifically triggers a key part of the brain. They call it the medial amygdala neurons, with a connection to another part of the brain called the hypothalamus. But what's different about this mechanism, unlike the other mechanism, is that it actually directly almost sends an electrical signal, kind of like turning on a light switch of stress, direct to the liver that flips on not just the breakdown of these stored glycogen molecules, which is how we typically think of stress-induced glucose elevation. But this mechanism actually shows that it can cause the production of glucose. So it seems that this novel mechanism is showing us something very unique, that our ability to mobilize nutrients during stress, typically for us to, as a survival mechanism, if we were running away from, again, a lion or a dinosaur or whatever it was, is actually twofold. Both the breakdown of glucose, but also this unique mechanism that it also facilitates the production of glucose from a direct brain to liver, almost electrical signal, nerve-based synapses from the top of the brain all the way to the liver, mobilizing glucose. And I think the implications of this are seen all over in the real world.
Yeah, thanks for the summary. And the other, people are probably going to overlook the joke about the dinosaur, but that would be a nice discovery if we were running from dinosaurs. That aside, yeah, I do want to double click on just how fascinating this is, because I feel like the clinical real world applications which we're going to get into, can get separated from what are just so fascinating scientifically. So to elaborate on what you said, we have this brain region that signals stress and then it communicates to another brain region. We typically think about it as changing the hormonal status of the body, activating the adrenal glands to release cortisol. What this paper found is something entirely different. So we won't necessarily go into all the details of the tools they used. I'll explain them in a newsletter I link below. But they were effectively able to show, like you said, a direct neural line from the brain to the liver that forced the liver to make sugar, completely separate from cortisol, adrenaline, and other glucoregulatory hormones. And if people just want a little bit of a glimpse into the methodology and how scientists dissect these pathways, it's super cool. So you can do, for example, genetic manipulations of animals where you express very particular receptors on these neurons. So you can specifically activate them and see what happens. So that's how you can separate it from, say, cortisol and adrenaline. And then you can do really cool things. If you want to determine the neural line from the hypothalamus to the liver, you can do experiments with engineered viruses. Some viruses, in this case, I think they use the pseudorabies virus, can move up neurons, kind of like they're climbing up a ladder. It's called retrograde axonal transport. So it's kind of blew my mind. I didn't really even realize we could do this, but you can tag a virus with a fluorescent protein, inject it into the liver, And then if there's a direct neural line to the brain, you can look in the brain for a glowy, glowy green signal. So this is the kind of methodology they used in this paper to unpack, yeah, there is a direct neural line from the brain to the liver. And then during stress, it tells the liver, hey, change your gene expression to make more glucose, de novo. So not even just breaking down the stored glycogen, but synthesizing it from proteins, circulating glycerol, lactate. So literally, this isn't an exaggeration, stress makes the liver make new sugar and then spill it into the bloodstream. Totally new mechanism, blew my mind too. Any further reactions on mechanism before I want to ask you about some of the real world implications from your clinical and personal experience?
I think it's important for the audience to appreciate how impressive this work is, because they went so far as to essentially put nerve-based stimulation through many of the ways you describe, but also almost, it's essentially like developing the ability to turn on and off parts of your brain, not just parts of your brain, but very specific regions of the brain where you can say, okay, I turn this on, we see this consistent effect, and we can turn it off. And then they went so far as to actually block other pathways that interact with it to very clearly show, hey, there's this elevation in glucose, and we know these factors are going to interact with it. Let's take each factor out one by one and show how this mechanism directly induces this effect. This is the beautiful part of science. If you read a paper like this, it's incredibly impressive to watch how they go about proving the impact of this part of the brain directly signaling glucose release. It's amazing and really well done.
I agree. And now I want to make things a little bit more concrete and clinical for people because, as we kind of alluded to but didn't say directly, this does explain or adds a layer of depth and resolution to things we see in humans. However, the methods they used, you just can't do these experiments in humans. You can't chop off human heads to stain brains, after an experiment. So necessarily these pathways are dissected using animal models. But they do give, like I said, new flavor and resolution to what we see in humans. So now I want to ask you, first, as a type 1 diabetic yourself, do you find stress increases your blood sugar? And if so, how do these findings shed new light on that phenomenon?
It's one of the challenges of type 1 diabetes, because with type 1 diabetes, for your audience, you don't produce insulin anymore. So everything you eat, all the changes in glucose, whether it be from a mechanism like this through stress, isn't immediately cleared by an automatic insulin release, like an automatic, like I say, computer algorithm that immediately sees a glucose elevation, immediately brings it down with insulin. So a lot of people may never know stress is causing their blood glucose to go up and then also their insulin to go up. But in type 1 diabetes, the only way to fix a blood sugar elevation, in this case stress, is you have to administer insulin. So it gives you this unique ability to give insulin when glucose goes up or not, to just see how the direct impact of something like stress can actually elevate glucose, removing the direct automated impact of insulin. And I've seen this a number of times. So one key example is I remember I was going to give this about 10 years ago, maybe it's not even 10 years ago, but it's coming up on it. I was preparing for a TED Talk. This is the last time this has ever happened to me in a public speech format. But this is very common for people doing public speech or some type of social environment where they fear something, whether it be social reaction or something along these lines, this mechanism. And I remember standing in front of, it wasn't even on the day I did the TED Talk. It was actually just standing in front of peers in a room, acting out what I was going to say. And it just felt so awkward, so uncomfortable. You feel almost like I'm being judged, which I wasn't, but either way. So you feel this. I remember my face felt the stress response. My heart rate went up. I started to feel the tingles in my face, all these clear signs that I would always feel with high levels of stress. And I watched my CGM precipitously rise 100 milligrams per deciliter over the next 30, 45 minutes. So a clear sign of this social stress. But I've also seen one of the telltale signs of this is in exercise. So very max effort sprints can elucidate a similar response where you're giving max stress onto the body in the form of physical exercise. And it's very common in kids with type 1 diabetes. Parents will often reach out and say, well, what do I do? Because my son goes up 100 to 200 milligrams per deciliter the second they walk out to perform their sport. Like it has nothing to do, they didn't do any exercise, the anticipation of it alone, or when they do a max effort sprint, they can see this. I've actually had a real world example of this on myself where I was on a very low carbohydrate diet. So my glycogen levels were already hypothetically lower. I was 20 hours into a overnight postprandial fast. I went for a 60-minute run. So in theory, my glycogen levels are pretty low here, Nick. So
Okay.
not probably zero, but very low. And I went for this run, and I could see at the end of the run, my blood glucose started to drop. And I didn't have blood sugar on me, blood sugar tablets on me, which are what you should always do, but I didn't. And I was about 20 minutes away from my house. And I'm like, oh man, I'm in trouble. So I actually used this mechanism, not knowing how it was actually working. And I sprinted. I went for a max effort sprint, 3 bouts of it, 30 seconds max effort, to the point where I was like, just like dying, gasping for air. And lo and behold, it elevated. Now, it didn't elevate 100 to 200 milligrams per deciliter, but it went up around 50 milligrams per deciliter.
I want to, sorry to interrupt, but I want to double click on apparently paradoxical but sensible what you did was. So effectively what you're saying was you, as someone with type 1 diabetes, was in a tricky scenario where your blood sugar was dropping and you were running back to your house. So one might think, oh crap, what do I do? It's a catch-22, rock in a hard place. If I continue to run, I'm going to cut through my glycogen stores and then I'll be in deep shit, so to speak. But I can't stop. So what? So what you did was you sped up. And what that did is it created a stress response to make your body make sugar, which it can do through, using alanine and other amino acids or lactate. So just the increasing lactate from your muscle glycogen stores. It's called the Cori cycle. You probably had a lot of muscle glycogen stores, which can't defend blood glucose. But if you use them, you can boost lactate, and the lactate can be turned via this, stress pathway in the Cori cycle into glucose. So it was a paradoxical kind of ingenious move to get yourself out of a really tricky and dangerous situation, if I'm representing this correctly. And then just to emphasize, why this is so important, particularly in you, but the clinical relevance here is when your blood sugar rises, and this is shown in the study from stress, could be it psychological or physical stress. Glucose goes up for the reasons we already explained, but insulin follows because a healthy human body will monitor blood glucose and try to keep it in this tight range. So this was actually shown in the study where, in the mice, when they stressed them out, the glucose went up and then the insulin kind of chased it. But type 1 diabetes is a pretty brilliant natural experiment, so to speak, because you don't have naturally the pancreas responding with insulin. You need to titrate it in. You need to have the knowledge to do that. So to bring in like a personal example, we did an experiment first year at Harvard Med where a bunch of us wore continuous glucose monitors. And I found what spiked me more than anything was actually being late to class. It created a stress response. I kind of ran over, so I had this little spike, but it was very acute. It would go up and come down. And it would come down, presumably, because my body's like, hey, all right, glucose in the bloodstream, let's give some insulin, get it back into the muscles. But if you have type 1 diabetes, or even if you have particular flavor of type 2, where you have beta cell dysfunction, you won't have that autocorrection. And a little stressor can end up with a huge spike that is then prolonged. So this is incredibly clinically relevant.
Absolutely. And to even piggyback off that even more is that, we know that there's a huge number of people who now are categorized as pre-diabetic. Actually, I looked at data from the Center for Disease Control over 10 years ago, and it was showing that over 50% of adults had prediabetes. That was 10 years ago, and things have certainly not gotten better on the general population level. So there's not only is it type 1 and type 2 do we see this example, but it also seems like people, those who are even at risk, is over half the population. And so, yeah, it's incredibly relevant for the majority of Americans. And we all know that stress can have negative impacts on our health, but we usually think about that from a psychological perspective, the burden it places on us. It's almost like this invisible backpack that's on our back all the times, and stress just puts more weight into that backpack for everything you do throughout the day. But it actually has a metabolic effect, as this paper shows. And this metabolic effect clearly illustrates that not only are you breaking down some of the stored materials your body has already for energy, but also it's making new forms of that same material in the form of glucose. And so the real world implications of this are real for the majority of people out there. And the health implications are also very real. I imagine one of the simplest and most powerful take homes is to reduce our overall stress, right? But I think
easier said than done. I'm sure we can both attest. But yeah. I mean, it's a nice visualization. If you're doing some sort of meditation or breathing, like you are literally changing a direct wire from your brain to your liver saying, hey, tamp down the glucose generation. So it's not just like fluffy, it's biology.
Yeah, and to piggyback off that, the psychological part of this is huge because you can't just drug this effect down, right? So there's things called beta blockers, which block the adrenaline or the epinephrine response specifically at receptors in the liver, which is the mechanism that we traditionally know, but it never completely abolished the effect. Okay. And everyone's wondering why not? I mean, if it's directly blocking the mechanism we know to be working, why is it not abolishing this effect altogether? And this paper helped explain in part why that might be, because the beta blockers were only addressing one part of the mechanism that we traditionally understood, which is the APA axis. But this new mechanism, it explains why there's still an effect that the beta blocker doesn't completely address. And we know beta blockers are commonly used for a number of therapeutic treatments, but actually a lot of people with type 1 diabetes use beta blockers to block this stress-induced effect around stressful events or around exercise. And this paper actually helps illustrate why it doesn't completely abolish the glucose-based effect. So it's quite fascinating.
I think we're going to keep piggybacking off each other. I have one more comment, then I want to go on to our next paper. But as you were saying that, I was thinking about how complicated and beautiful this gets. And so another factor to bring in is something like a metabolic state of obesity. One thing we actually know is that, at least from animal models, that obesity fat tissue releases certain hormones like leptin, which can remodel the blood-brain barrier around the hypothalamus, which is the feed-in point from the medial amygdala en route to the liver, and then in that way change nervous system tone. So you could be amplifying the negative metabolic impacts of stress via this mechanism by having excess fat tissue in the hormones that fat tissue produces. So it is kind of like a moment when you start to like elaborate on what this mechanism could really mean. But with that, I do want to get on because we have so much to cover. Another study published this year, 2025, in Nature Medicine, was looking at the glycemic responses to different foods. Now, that's one thing. What I actually wanted to ask you about is glycemic mitigators. So, what are glycemic mitigators? Fat, protein, fiber. These are things that in general you can eat before having a certain glucose load that will lower your blood sugar spike. So if you eat fat, say, before eating some amount of carbohydrates, say you have buttered eggs before you eat a sweet potato, the spike will be lower. And it's actually the same for fiber. But one of the really interesting results of this study that I wanted to pick your brain about was how this interacted with pre-existing insulin resistance. So one of the things they found was that in people with insulin resistance, they don't get the same blood sugar protective effects from things like fiber. So if you're insulin resistant and you have fiber before a carb load, the fiber quote unquote benefit on blood sugar will be less. Whereas for someone who's insulin sensitive and healthy, the fiber probably, say, before a bowl of grapes would reduce the spike. So it's kind of a 1-2 punch because you're already insulin resistant. The carbs are going to spike your sugar an amount, and then the insulin's going to fall and you're going to have hyperinsulinemia. But in this case, the quote unquote protective food variables aren't as protective. What do you think about that?
Well, number one, I think anytime you see something like this, the first thing you assume is, why is this happening? Because just like the prior paper we're talking about, if we understand why, it might help us understand how to apply it with all these interactive mechanisms happening at the same time. And historically, we would think, okay, that might be a microbiome effect, right? Because the microbiome places this almost barrier in the gut between the food and the intestinal absorption of it. And so it places this kind of interactive barrier that processes various components of the food in particular ways. And that has been kind of a lot of the recent focus because of this emergence and interest in how fascinating the microbiome is and all this emergent evidence on and all sorts of model systems of how powerful it could be on overall health. But one thing you mentioned that's very important is that often has been brought up at the expense of understanding the metabolic physiology or the metabolic status of the individual themselves as well as a key determinant factor. Because we've even actively we're running a study for the Department of Defense right now where we recruited a very consistent cohort, all males, all similar BMI. The tightness of this cohort was their 21 years of age, average mean 21 years of age, standard deviation 2 years. Super tight cohort. Yet if you look at their basal insulin levels, they differ almost sixfold. So even though you look at someone and think, oh, wow, they're probably similar equivalent health, there could be wildly different metabolic effects in the body. And insulin is just one example. But what's really cool about this study is they took it a step further and actually used a tool called continuous glucose monitor and was able to utilize that real world tool something that anyone could, in theory, go buy right now, as long as they sell them at your local pharmacy, or you can get a prescription if you happen to have diabetes. And they found these unique differences across all these individuals, those who are at risk for or maybe have diabetes. And what I find interesting about this paper is, for me at least, my interpretation of it was, yes, there was this unique effect of the lack of, or the reduction in protective effects once someone has diabetes. They were showing that on the average, someone with type 2 diabetes may not see the same level of protection from fiber, or the same level of protection from other nutrient ingredients that we associate with health, or you can co-consume them with other foods, and they'll blunt maybe some of the negative effects of some food compositions or some dietary strategies. What's the actual implication of this, Nick? I think one of the most important implications of this is that what would someone do if they had diabetes? Because we are told to eat fiber. We're told to take some foods and maybe mix them together with other healthier foods, like, let's say, protein, or maybe swap forms of food for other forms of food to improve our overall health. And I don't think this paper says not to do that. I think what this paper essentially illustrates is that there are categories or subgroups of individuals that are particularly at risk for higher glucose spikes, even though you're adding some of these tools and strategies into them. But what I think this paper also showed, by illumination of these fascinating tools called continuous glucose monitor, is that you can monitor your own glucose response as an individual N of one experiment and see your personal response. Because this is probably a bit too controversial, although you do a good job of balancing that out well, Nick. No one got diabetes from a flat glucose curve. Okay, no one gets diabetes with a flat glucose curve. And so if you're seeing that you have these wild, crazy spikes with certain foods and not others, you can lean into the foods that you seem to have better glucose responses to. And it doesn't mean that you're going to get diabetes because you have a normal glucose response to certain foods. But if you have a wild spike and some of these individuals were going north of 200 milligrams per deciliter, that would be concerning. Those levels are associated with adverse effects.
So I'm going to first emphasize the clinical importance, which you so correctly pointed out, and then another deeper level of the science here. First, neither you, I, or the researchers are saying, hey, fiber is quote unquote bad if you have diabetes. I think what we're trying to combat, if you don't mind me hopefully not speaking for both of us, but it's worth speaking for both of us, is that the platitudes that are put out for the general population, like, oh, fiber is better, oatmeal's okay because yes, it has carbs, but there's also the fiber that balances it out, is not serving public health because it's very contextual. So people should know, hey, if you have insulin resistance, I'm not saying oatmeal's bad, be all end all. But this idea of, oh, it has fiber and that will protect you, it changes based on your metabolic circumstance. So that's clinical implication 1. Clinical implication 2 is actually just has to do with the overall individuality and heterogeneity of blood sugar responses to the same foods. And this isn't new research. This has been documented at least for 10 years, where, there's research showing if one person eats a banana and one person eats a cookie, they can have totally different glycemic responses to it. So there's a lot of individuality, but you can dissect that with continuous glucose monitors, which is a great tool that's now available over the counter. And then the third element is the level, scientific level deeper, is, well, then how can we use those clinical tools to feed back on the science? And one of the things this research group is doing that is really brilliant is using AI and machine learning to find signals in the personal data that inform the underlying pathophysiology. So one example that I'm sure you picked up on, but we should just give it because it blew my mind, was the potato to grape ratio. So basically what they found was that, people with insulin resistance seem to preferentially spike more to potatoes relative to, in this case, grapes were a big spiker. So you could have grapes as a control. So basically, and they actually gave me a protocol, which I'll link below, you could wear a CGM and then measure your peak spike to potatoes on one day versus grapes on another day, ratio those, and those will give an indication of your level of insulin resistance, which is scientifically just freaking cool.
What's cool about this is it actually is trying to tie kind of these advanced laboratory-based assessments into real-world applications that almost gives the power back to the individual, right? Because a lot of times you're beholden to going to a doctor, getting a single test at one time point, maybe hopefully every quarter, maybe only every 6 months. And then for some patients, you're lucky if you get it once a year. But this gives you insights every 5 minutes, over 24 hours, over weeks and weeks and months if you continue so. And that type of resolution gives you insights that are incredibly empowering and guides decision making that's so individualized to your personal response. And it also illustrates that just because something is quote unquote healthy doesn't mean it is for you. I think that that's important to appreciate. And again, we're not widely saying that potatoes are inherently unhealthy or anything like that. But what it is illustrating that on the average, if you have diabetes, you may fall into one of these buckets more often on average. But if you were to take this away and try and be actionable with it, you don't want to assume that. You want to actually find out, hey, look, if I respond to certain foods by assessing it for yourself, that's going to be your best indicator of how you respond, because we're all slightly different humans. I mean, look no different than me and Nick. I mean, he's got this amazing beard. Mine's not quite as good. He's got different color hair. You can't tell, but he's actually much taller than me as well. I think he's like 6'5", 6'7". All these individual differences that come out there. And so I think at the end of the day,
How are you really? I don't know if people are going to be missing this joke. I'm like 5'7", 5'8". You're what, 6'3"?
Maybe 6'5", give or take, It's so, but it really.
We can get in person and take a side-by-side photo for the thumbnail.
I don't know if we do have one. We'll have to definitely get one.
No, we have we met in person?
Yeah, we had Metabolic Health Summit some years ago. Yeah. I mean, it definitely shows that, there's clear group differences, but you can test for yourself. You can be your own experiment, see how you respond to foods, and really eliminate the uncertainty of what's best for you using tools like a CGM. And it also helps illustrate, in my mind, that your metabolic status does predict better or worse responses on the average. And finding that out might be very helpful. You can get things like ask for fasting insulin, ask for fasting glucose, maybe get a HOMA-IR score, look at your HbA1c. These aren't sufficient alone, but obviously as this paper illustrates and other papers that we're going to talk about do. But essentially what they show is that, foods like fiber and protein, they tend to do better for most people, but it doesn't mean that it's always universally applicable. And that goes to show where the science has been going for quite some time, which is the personalized medicine, which is getting to the individual level and helping people empower themselves, which this paper has shown, with tools that you can actually apply in the real world, which I think is really, really powerful.
I have one more question on this line of research, actually a separate paper, then I'm going to save the rest of the goodies for part 2. But so this was a 2025 Nature Medicine paper. Prior to that, there was a precursor paper on this population published in Nature Biomedical Engineering in 2024. And what they did in this study is they used continuous glucose monitors and machine learning to decode 4 flavors, 4 causes of, in this case, type 2 diabetes, although it overlaps with type 1. So I'll list them. There is muscle insulin resistance, liver glucose dysfunction, incretin dysfunction, which is like GLP-1 hormones, and then beta cell dysfunction, which actually overlaps with type 1 diabetes. So there's a little bit of a Venn diagram going on here. But what I found very fascinating was this bucket of incretin dysfunction. Now, again, incretin, GLP-1 hormones. These are hormones that are important for glucose homeostasis, and they're also the basis for this generation of weight loss drugs. Ozempic, Wegovy, they mimic GLP-1. They do it at a much super physiological dose, but the point is they act on this axis. Now, putting 2 and 2 together with other research. So other research has shown that certain medications that are commonly prescribed, in this case statins, the most common statin being atorvastatin or Lipitor, can in human trials plummet GLP-1 levels. So this is all new research, but you can see, maybe people are putting 2 and 2 together already, it begs the question, if there are particular causes of diabetes that we can now dissect at the individual level, and human data on how certain pharmacotherapy, including statins, can target this pathway, then one would reasonably hypothesize, hey, there's going to be a whole type, a whole species of diabetes that will be enriched in, say, people taking statins or other medications that lower GLP-1 levels. So I had a conversation with the senior author of this research, who himself had diabetes or pre-diabetes. He had the beta cell dysfunction type. But I asked him, do you agree this population of people with diabetes who have a GLP-1 defect that's driving the diabetes might be enriched in, say, statin users? And how does that implicate care? That was me on my soapbox for a little bit, but as someone with diabetes and a fellow researcher, I wanted to get your perspective on this possibility and what it means for clinical care.
This paper elucidates something incredibly novel. We have known for some time there's different forms of diabetes. What this paper illustrated was, four different stuff, because we traditionally bucketed them in three, and this illustrated four, as you really well articulated. And of the first two, the muscle and hepatic insulin resistance accounted for around, I think, 34%, and then the incretin-based and the beta cell dysfunction-based ones around 40%, so actually a higher percentage of the overall group, that then place individuals at risk for the development of type 2 diabetes. And this leads to this idea, because we've known for a while, controversy aside, that statins can place a certain number of individuals who consume them at risk for diabetes. It's a known risk factor of statins. The idea of statins, of course, most of your users would certainly probably know this, is that the idea is that would lower your cardiovascular risk. It's believed to do that through LDL, but there's also other mechanisms through inflammation pathways, et cetera, that are hypothetical. There's a lot of nuance there, but that's the reason people would often prescribe them in a medical setting for that logic. But we also know that there's evidence that in some scenarios, particularly this paper you highlighted, that it can increase, glucose intolerance and diabetes risk in some humans. And as you pointed out, this illustrated a very powerful, it was actually really clear effect on GLP-1s and an increase in a subsequent HbA1c, which is a 2 to 3 month average of blood glucose levels. And why that's important is because when we think about overall risk for long-term, disease, like cardiovascular disease, we think about them, at least I do, in hierarchy. What matters most to overall risk? And we know that diabetes, or the elevation and usually defined by the elevation in blood glucose in almost all of these analyses, and in this case, HbA1c, is by and large a much more powerful risk factor, multifold larger than anything else typically is, as far as hierarchy and risk for the number one cause of death, which is cardiovascular disease. This paper illustrates that there are certain drugs that come with, honestly, everything does, with a risk to benefit ratio. There's no decision in life that doesn't come with a positive and negative ratio. You always hope to maximize the reward and minimize the risk in every scenario, but it clearly illustrates that there's no free pass entirely in life. And there usually never is when you take something that directly blocks particular pathways, like a statin does. And so you'd expect some type of off-target impact. Now, what I think this illustrates, though, is that this research group, once again, in this paper, also illustrated the ability to subgroup phenotypes based on CGM profiles. This, again, allows for it just by monitoring with these wearable tools at home. Obviously, if you have their computer algorithms, which I'm sure will eventually get to light of day for people to utilize, will allow them to understand their potential type of risk. And then they can make more informed decisions. And I thought another aspect of this that was particularly interesting is the relationship with the microbiome. And, we often think of the microbiome as kind of this very complex, novel, very interesting area. But it also, there's a lot of things we know on the average tend to improve what quote unquote good microbiome health, which is kind of a quotes around it because it's kind of it's all subjective to the outcome you want. But ultimately, what we're targeting here is precision medicine. And the best way to do that more than anything isn't to just rely on average outcomes. This is just telling us, oh man, if I take a statin, I need to be careful about my glycemic control, or if I make that decision with doctor-patient relationship environment. But ultimately, self-testing and responsiveness is a critical part of this. And if you are going to take something that puts you at risk, understanding that it appears to be through a mechanism that might be microbiome related, maybe you want to improve your overall microbiome health and kind of consider the implications of things like, I don't know, fiber, like exercise, like good sleep, all things interact.
Sorry to interrupt, but they get quite specific in the statin paper where, like you said, the microbiome is a little bit of a black box.
Yes.
But you can look at the metabolome of the microbiome. So rather than saying, what the gut bug is, which isn't necessarily that informative because every ecosystem is different, what are the metabolites generated? Because these are the arsenal. These are the action and points, the places to intervene because you can measure them in the bloodstream. What is the microbiome making? In this paper, they actually showed it was a secondary bile acid called UDCA, which they could supplement back and basically reverse the negative effects of statins. As you were saying, this is really important clinically. And I think to demonstrate that, just imagine where medicine could be in 5 years. So I know the Snyder Lab, the ones that did this research, are trying to make this publicly available. So now imagine you have a CGM on and you have an app on your phone. you are at high cardiovascular risk. Maybe you've had a heart attack, so your doctor puts you on a statin for a medication. The app could detect not just an increase in glucose, but a particular shape of that glycemic curve that could indicate, hey, not only are you developing insulin resistance or type 2 diabetes, but you're generating it of this particular flavor of diabetes. And that could be a contraindication or at least inform future action, changing medications, taking, compensatory supplements like a TUDCA or UDCA. And I'm not making medical claims here. I'm just saying, like, that is why this research is so important to talk about, because we are shifting from these platitudes of, hey, lower is better, more fiber is better, yada, yada, to what's going on in you. And these tools, I think, are like really around the corner. We already have the tools. It's just like the CGMs. We're just like folding them in with large population data sets and using machine learning and AI to make this interpretable and actionable at the clinical and individual level. And I think that is really exciting. Not to put value judgments, broad value judgments on any food or medication, but like you said, risk benefit analysis. And the art here is that at an individual level, the risk benefit analysis doesn't just line up with large population data sets on either side or large population findings. So we are refining that, and it will give people the power to make much more informed individual choices and iterate on them in real time, which I think is pretty cool.
So I couldn't agree more, Nick. And I also think it's going so far as to potentially inform medicinal therapies in a clinical setting, because knowing the form of or flavor of diabetes, as you put it, directly impacts historically how we know people respond to certain treatments like metformin, like lifestyle, such as exercise and beyond. But there are some interventions that kind of sweep the whole gamut, like some of these like diets, like very low carbohydrate ketogenic diets. But if you're going to do a medicinal therapy like metformin, or physical activity, the type of diabetes has historically illustrated a likelihood to be responsive to those treatments. And so understanding why, which I think you do a great job, Nick, of illustrating for those out there trying to learn more, empowers you. There's no way around it. It empowers you as an individual when you understand why things are happening, so that when you hey, I want to try this, your doctor says, hey, do you want to try statins? Or hey, do you want to try metformin? Are you someone who your flavor of diabetes would put you as a potential beneficiary of that? Because there's always a risk with everything you do, no matter what. Even if you exercise, there's a risk, right? And so that I could not. I know, as someone living with diabetes for almost 2 decades now, you want to be empowered. You don't want to feel like your disease is just in control of you, or that someone else is making all the decisions for your health. You want to feel like you're empowered at an individual level. And I think almost every healthcare provider out there would also want their patients to take the bull by the horns and take action using helpful and evidence-based resources. So I think you do a great job, Nick, at doing that with your platforms.
Appreciate that. Well, speaking about platforms, I'm going to push the rest of our discussion into part 2, where I'm going to tease, we're going to talk about what I thought was the coolest fiber paper. We were shitting on fiber before. Now we're going to give it some praise. The coolest fiber paper I've ever read. Some potential risks about long-term ketogenic diets, maybe not, and some more practicals as well. So before we sign off on platforms, where can people find more about you and follow you?
I'm on X and Instagram. X, I'm on Koutnik, and then Instagram, Andrew Koutnik PhD. I also have a website, andrewkoutnik.com. And if you want to follow for information, there's Substack and YouTube as well, where you can find a lot of helpful resources.
Thanks so much. Everybody come back for part 2, which will actually be my 4th interview on this channel with Andrew.